Let's warm up. We want to rewrite the following expressions as mixed radicals in simplest form. This one's already a mixed radical, but it's not a mixed radical in simplest form. There's still a perfect square in here. Now, if you know your perfect squares and you can just factor them out, that'd be great. So 25 is a perfect square. It's a factor of 75, and so we could just split it up and split it up even more so that it's under its own radical sign. You don't need to do this. I'm just showing you the steps that would be happening. Take the square root of 25 and it's 5, and the square root of 3 has to stay in there because it's irrational. So 15 root 3. Now these two should be the same. You can confirm that on your calculator as a decimal approximation. Now if you couldn't think of the perfect square that's in here, we look at the index, which is 2 by default, and we're trying to find groups of 2. So if we factored 75 into 5 and 15, and then 5 and 3, we'd be looking for pairs. And so if we have two 5s, that's a pair, and that's together a perfect square. So that's why I separated 25, because there was two 5s, and the 3 is by itself, so it's not coming out. Next one. Now we just have variables in here, so we really need to know what how things pair up. This is the square root, so we're looking for pairs. So we can separate it into pairs, like C has a pair and D has a pair, and then C has one extra that's not going to come out. And then we can take the square root of C squared, it's just C. We can take the square root of D squared, just get D, root C. Now the next one, we've got a cubed root, so we'd be looking for groups of 3. So let's factor 24 and look for groups of 3. There's 2 and 12, 2 and 6, and 2 and 3. That means these 3 2's here are a perfect cube. So we can put them together. And you can write it like 8 or 2 to the power of 3, because there's 3 of them. There's an extra 3 here that's not going to be perfect, so we'll leave it in there in the radicand. Q, well, we want 3 of them to make a perfect cube, and there's 2 extras. And always put an equal sign, keep going. This is just 2q, and this is the cubed root of 3q squared. Biggest mistake is forgetting the index. Make sure the index is sitting in the little seat of the radical, or it will look like a coefficient. Next one, we've got fourth root, so let's factor 81 to look for groups of 4, and this one's 9 and 9, and 3 and 3, and 3 and 3, and so 81 is a perfect number for this one. So 2 fourth root of 81w, we're looking for groups of 4, so 8 would be the largest. We could have 2 groups of 4 here. And then what's left in here? Well, the leftover w squared. And we've got 2 times this fourth root of 81 is, and I could have wrote 3 to the power of 4 here if that helps you remember, but it's just 3. And the fourth root of w to the power of 8 is just w squared. And the fourth root of w squared is irrational, so it stays in there. And then 6w squared fourth root of w squared. 5.1, we want to add and subtract radicals. It's going to work just like adding and subtracting everything else in math. We can only add and subtract like terms. So here we have 2 phi plus 5 phi, and they're the same, so we've got 7 phi. 35 phi minus 12 phi minus 10 phi is 13 phi. Because they're all the same, they're all like terms. 3 phi minus 12 phi, negative 9 phi, plus 28 psi, and that's of course not the same, we can't put them together. Now radicals are going to work just like that, except instead of a phi, we're going to have a radical like root 2. And so it'll work like 2 root 2 plus 5 root 2 is 7 root 2. For radicals, they need to have the same index to be the same, so a square root of 2 is not the same as the cubed root of 2. Let's give this a try. First one's very easy. 8 root 3 plus 4 root 3 is 12 root 3. Minus 5 root 3, we're just left with 7 root 3's. For this one, we want to add these together, but they look all different. So we need to change these into a mixed radical and simplest form and see if they can start looking the same, so we can actually put them together. Now we're looking for perfect squares because this is a square root, or pairs of numbers if we have to factor it. For 48, I know that 3 times 16 is 48, and 16 is a perfect square, so I'll break it up like this. Next one is 180. Now 180 is a larger number, and let's factor it and look for perfect squares, because we probably don't know instantly what the perfect square in there is. So we've got 2 and 90, we've got 2 and 45, we've got 9 and 5, and 9 breaks down to 3 and 3. So these two 2's and these two 3's make a perfect square because they have pairs. So 2 times 2 times 3 times 3 is 36. And the 5 has nobody there. Next is minus, and the both need to be minus. We'll distribute in the minus sign there. This one's pretty easy. 4 is a perfect square, 4 times 3, and 3 is not a perfect square. And last one, 9 is a perfect square, and 5 isn't. 9 will be coming out, not the 9, but this will take the square root of 9, and 3 will come out there. The square root of 16 is 4. The square root of 36 is 6. So far, these two are different radicals, so we can't add them. Square root of 4 is 2. And square root of 9 is 3. And so we're going to multiply 3 by 6 by the coefficient that was already out here. And don't forget about that coefficient. All right, now we've got a couple that are the same. This is a root 3 and this is a root 3. So 4 root 3's minus 2 root 3's. We're going to be left with 2 root 3's. Then we have 6 root 5's and minus 18 root 5's. So 6 minus 18 is minus 12. And last one, these are cubed roots. So it'll be even more difficult. We're looking for a perfect cube. And 16, well, I know 8's a perfect cube, and 8 times 2 is 16. For 54, that would be 27 times 2. And make sure your vinculum covers the whole radicand. And last one is 250. And that would be 125 times 2. And let's actually take the cubed root of 8 now, which is 2. This 2 here stays in the radicand because it has no triple to be with. This is the cubed root of 27 is 3. The 2 stays in there because he's all alone. And the cubed root of 125 is 5. Cubed root of 2. Now, it looks like these ones all were the same, so we're going to be able to add and subtract all of them together. So 16 cubed root of 2 minus 12 cubed root of 2 plus 5 cubed root of 2, and we put all those together, we get 9 cubed root of 2. Example 2, we want to simplify this radical expression. It's got a variable in it, so we'll have to deal with that, but we deal with it the same way. So we're looking for perfect squares, so 4 and x squared. And 4 times 5, and there was one more x here. So these guys are all perfect, and these guys are not, they will stay in there. Minus 3 9 is perfect, x squared, and the 5 is not, and there's one more x. Now we want to take the square root of this, take the square root of that. So the square root of 4x squared is just 2x. The square root of 9x squared is 3x. Now 3 is already out there, so 3 times 3 is 9. Okay, so that's not the 9 that's coming out. 3 came out times 3. And now 2x minus 9x. The radicals are the same, so we can actually subtract those. And then we want to say, if we want real numbers here, we'll keep this restriction here, x is greater than or equal to 0. For example 3, I'm going to do the same thing. Okay, so 5, find the perfect squares in here, and just everything else that's not perfect, leave it in there. 25y squared and 3y stay. Nine y to the power 4, 3, one more y. $25 and 2x. Alright, so I got all my perfect squares lined up. So 5 times 2x. 5 times 4 is 20. The square root of y squared is just y. It comes out here, multiplies with that y. And then the 3y is left in. We've got square root of 9 is 3, times 2 is 6. Square root of y to the power 4 is y squared. And square root of 25 is 5. That's minus 15x, square root of 2x. And now we'll just see what we can put together here. This one's square root of 2x, and this one's a square root of 2x, and it's got a 15x in front and 10x. So we can put those two together, get minus, so 10 minus 15 is minus 5, x square root of 2x. And these two radicals are the same, as well as this variable in front, so 20 minus 6 is going to be 14 y squared square root of 3y. Now we want to have only real results. So we have an x under the radical here, and we can't take the square root of a positive number if we want real results. So we need to say that x is greater than or equal to 0, and also y is greater than or equal to 0. Same deal for this question. We want to find the perfect cube in here. Well, 27 is the perfect cube. That's 3 cubed root of x squared. 8 is also a perfect cube, so we can take the cubed root of 8. And 64 is also a perfect cube. That's just 4. And x squared. So all of these have the same radical, so we can add and subtract them. So 3 minus 2 is 1, plus 4 is 5 of these radicals. Identify any restrictions. Well, this time we look at x and it's under the radical sign, but we're taking the cubed root. So we can take the cubed root of any number and get a real answer. And so there's no restrictions. So we can just write that x can be any real number here because it's under a cubed root. Example 5 is cubed root again. So we're looking for perfect cubes in here. So let's separate those out. 8 is a perfect cube and v cubed is a perfect cube. What's left? Well, a 2 and 2 more v's. Next one, 3 is not a perfect cube, but w cubed is. and there's 3 left, and there's a w that we didn't use. Next, there's a 2w already in front of this one. Okay, there's an 8. That's a perfect cube. Looks like that's it. That leaves the 3w inside here. 5v, cube root of 54, so 54 is divided by 2 is 27, and the 2v squared is not a perfect cube. Let's actually get these perfect cubes out now that we've separated them. So we've got 2v, cube root of 2v squared is still in there. We've got w, cube root of 3w. We've got cube root of 8 is 2, so 4w, cube root of 3w. And cube root of 27 is 3, 3 times 5 is 15v, cube root of 2v squared. And now let's collect up like terms. So we have a cube root of 2v squared, we have a cube root of 2v squared, with a v in front, with a v in front. Those look good. So we've got 2 plus 15 of those is 17v, cube root of 2v squared. We've got a cube root of 3w, cube root of 3w, and with w in the front, so 1w plus 4w's is 5w's, cube root of 3w. And since we have the cube root for all of these, then both our v and our w can be any real number. Example 6, we have a square with area 24. That would be this one. And it's placed beside a square with area 50 square units. In simplest form, write a radical expression for the perimeter of the shape shown below. So we need a side length. Now, to find the side length of a square, we have the formula area equals side times side, or side squared. This, we know the area, we don't know the side. So we can take the square root, both sides here, and get the side is equal to the square root of 50. Now, normally we'd get plus or minus because we took the square root of a variable squared, but we don't want the minus case. It's inadmissible. We don't want a negative linear side measurement. So we have the side as root 50, and we can do better than that since it wants it in simplified form. We can take out the perfect square in here, 25. The square root of 25 is 5, and the root 2 remaining in there. So this side here is 5 root 2. This side is 5 root 2. This side is 5 root 2. We'll do the same thing for this side. So we have the area equals the side squared. Area is 24. Side squared, that means the side is the square root of 24. We can do better than that. Side is equal to, there's a perfect square in here, 4. So the square root of 4 is 2, and a 6 still inside. So that means this side is 2 root 6, this side is 2 root 6, this side is 2 root 6. Now we just need this little edge piece here. It's 5 root 2 minus 2 root 6. So the whole thing minus the tiny green side here. And now we're ready to add it all up to find the perimeter. So the perimeter is equal to, we'll just count up the 5 root 2. So we've got 1 of them, 2 of them, 3 of them, 4 of them. So I'm just going to go, we have 4 of them. And then we have 1 of these, 2 of these, 3 of these, minus 1, so back to 2 of those. And we can multiply. We've got 20 root 2's and 4 root 6. And since we don't have any units in this question, that would be our perimeter. Example 7, we want to find how long this red line is in exact values if one of these yellow squares is 1 centimeter square. So 1 centimeter by 1 centimeter. Now we could do this as individual pieces. We could extend this down and this over, and or we could do it in one big piece. Either way would work. So let's do it in one big piece first. So we see if we make a giant triangle here all the way down, and a giant triangle here, this would be 1, 2, 3, 4, 5, 6 units, or 6 centimeters. And same with this one, 6 centimeters. And then we want the red line, so it's just c squared is equal to a squared plus b squared. In this case, a squared is 6 squared and b squared is also 6 squared. So c squared is 36 plus 36, or 72. We'll take the square root of both sides here, and we get c equals. Now normally we get plus or minus because we took the square root of a variable squared, but we don't want the minus. We don't want any negative linear measurements here. And the square root of 72, there's a perfect square in here, it's 36. So I could break it apart if I needed to show that step. 36 times 2, and the square root of 36 is 6, and the square root of 2 we'll keep in there. This question does have units, it's centimeters, so we'll leave that there. Now the other way we could have done this question is by little piece. So if each one of these centimeters are 1 by 1, then we could find that. So this time our c squared equals a squared plus b squared would be just 1 squared plus 1 squared. And our c squared is then equal to 2, and c equals the square root of 2. And then we can just say, well, we've got 1 of them, 2 of them, 3 of them, 4 of them, 5 of them, 6 of them. And so our red line is 6 of these root 2's.
Yay!